You probably think that complex numbers and functions are useless in practice, that phasors and imaginary impedances of capacitors and inductors are just mathematical curiosities that you unfortunately have to learn. So you'll be surprised to learn that complex signals are actually practical, and most of this course will be dealing with complex functions starting with Fourier analysis to system transfer functions and frequency response. Imaginary numbers allow very elegant and simple representation to deep and complicated relations among signals. There is no such real number, the square of which will be negative. But it is convenient to define a mathematical object which is called j, imaginary number, equals to square root of -1. And basic arithmetical rules for that object also should be defined. This is convenient for solving equations and simplifying notation. We define the complex number c equals a plus bj, where a is a real part of c and b is imaginary part of c. You need to note that imaginary part of c is b and not b multiplied by j. So when you compute an imaginary part, you need to write just b part, it's just the real number b. Also, we could define different powers of j. For example, j to the power of 0 is of course 1, because any number to the power of 0 is 1. J to the power of 1 is j itself, j squared is -1, by definition of j, because j is square root of -1. J cubed is minus j, because this is -1 multiplied by j, and j to the fourth power is 1, and then the pattern repeats itself all the time for higher powers. We have also a graphical representation for complex numbers. The horizontal axis is real and vertical axis is imaginary. For a better intuition, you could think about C as the point AB in rectangular or Cartesian system of coordinates, or as a vector pointing from origin to AB point. The addition, subtraction, multiplication, and division of complex numbers all follow similar actions on the vectors. So if you know how to do addition, subtraction on vectors, you can do them also on complex numbers. This is exactly the same. We can start with addition and subtraction. If you want to add two complex numbers C1 and C2, or to subtract them, so it's C1 plus minus C2 equals, then you're writing them in rectangular form, A1 plus B1j plus or minus A2 plus B2j. Now, if you're opening parentheses, this is what you get. You get A1 plus or minus A2, depends if you're doing addition or subtraction, plus B1 plus or minus B2, depends on addition or subtraction, multiplied by j. And this is the result of addition or subtraction. For vectors, it is known as parallelogram rule. So if we draw two vectors C1 and C2, and we want to add them, then we get that parallelogram rule and adding them graphically like that. If you want to subtract them, it is very easy to remember the direction of the arrow. So arrow will connect basically C2 and C1, but you need to remember the direction of the arrow. Arrow should look from C2 to C1. Why is that true? It is easy to remember the direction of the arrow in subtraction, since following the path from C2 plus vector which is C1 minus C2, which is connecting C2 to C1. C2 is cancelled, and then we get C1 vector. So we basically check in subtraction by addition. We should arrive at C1, so the vector should point from C2 to C1, and then this will be vector C1 minus C2. If we want to multiply C1 by C2, we're just doing that the regular algebraic way, and then we need to note that A1 plus B1j multiplied by A2 plus B2j equals, we're using distributive flow here from algebra, and multiplying a1 by a2 plus b1, a2j, and so on, until we get 4 different terms here. We need to note also that j squared by definition is minus 1, and then we can combine similar terms and to get a1, a2 minus b1, b2 plus, in parentheses, b1, a2 plus a1, b2 multiplied by j. For division, we're doing something similar. If you want to divide c1 by c2, it's equals a1 plus b1j divided by a2, b2j. We need to use some simple trick here. And the trick is to multiply numerator and denominator by a2 minus b2j, which is, we will call it conjugate later. Now, if you multiply the bottom part, which is denominator, by that conjugate part, we will get real number. And then, on the upper part, we have regular multiplication. Let's see how it works. So we will have a1 plus b1j multiplied by a2 minus b2j divided by a2 plus b2j multiplied by a2 minus b2j. At the top, we will be left with a1, a2 plus b1, b2, which is real part, plus the imaginary part, which is b1, a2 minus a1, b2 multiplied by j. So the bottom part, which is denominator, will be a2 squared plus b2 squared plus b2a2 minus a2 b2 multiplied by j, which is basically 0 because b2a2j minus a2 b2j is 0. So we will have only a2 squared plus b2 squared at the bottom of that overall expression. As we have seen, multiplication and division are not very convenient in rectangular domain or Cartesian form. Polar representation is more convenient. It is completely equivalent to the rectangular one and based on a simple trigonometry. Okay, let's say we have real axis, imaginary axis, and some vector with radius r and angle theta, and the coordinates of that vector is ab. So we have complex number a plus bj, and we want to represent that in terms of radius vector and the angle. So how can we convert into the polar representation? Clearly both are completely equivalent. So tangent of theta by definition will be b divided by a. So theta could be computed as arctangent of b over a, or inverse tangent. Now, radius could be computed using Pythagoras theorem, and it will be square root of a squared plus b squared. If you want to go back and to define a and b as a function of r and theta, so we want to convert polar representation into the rectangular representation, all we need to do is to use trigonometry. Since we know that cosine theta is a over r, then a equals r multiplied by cosine of theta. Now, we know that b over r is sine of theta, so b equals r multiplied by sine of theta. So from now on we can represent a plus bj as r with angle theta, but also we can represent that as r multiplied by exponent of j theta. Now, why is that true? It follows from Euler theorem that we will develop right now. Euler theorem states that e to the power of j theta equals cosine theta plus j multiplied by sine theta. Now, if we replace theta with minus theta in the same theorem, we can get that e to the power of minus j theta is cosine of minus theta plus j sine of minus theta. But since cosine of minus theta is the same as cosine of theta because of the symmetricity of that function, and sine is asymmetrical, so sine of minus theta is basically minus sine of theta, we can write that e to the power of minus j theta equals cosine of theta minus j sine of theta. Now, if we solve those two equations, Euler theorem equation and that e to the power of minus j theta equation, we can compute what is cosine and sine in terms of those complex exponents. So cosine of theta will be equal to e to the power of j theta plus e to the power of minus j theta divided by 2, and sine will be e to the power of j theta minus e to the power of minus j theta divided by 2j. So that way we can represent cosine and sine real functions with complex exponent functions, and we will use a lot of that in the future. But it also shows that you can use radius multiplied by exponent of j theta, because this is nothing else but r multiplied by cosine of theta plus jr multiplied by sine of theta based on Euler theorem, as representation for polar complex number. Multiplications, divisions, powers and roots of complex numbers in polar representation are much easier than rectangular representation. Let's see. If you want to multiply one complex number r1e to the j theta 1 by another complex number which is r2e to the j theta 2, it will be equal just multiplication of the radiuses and sum of the angles. Division is similar. It will be, if you want to divide one complex number by another in polar representation, you just need to divide the radiuses and to subtract the angles. For the power, you making power of the radius and multiplying the angle theta by n, which is the power that you want to put your number r, e to the j theta. Root is the opposite one, so it's power of 1 over n, which means that will be r to the power of 1 over n, which is nth root of r, multiplied by e to the power of j theta over n. Specifically for square root, you have square root of r multiplied by e to the j theta over 2. Now you also have geometric representation for the multiplication. If you want to multiply r1 to the exponent of j theta 1 by r2 to the exponent of j theta 2, all you need to do is just to draw r1 with the angle theta 1 and then to rotate that vector counterclockwise by the angle theta 2, and then multiply that r1, the length of that vector, by r2, and then you get the multiplication of first number and second complex number. Also you have very simple graphical representation for the exponent of j theta. So what it means is just point moving on a unit circle. Let's say you have some unit circle with radius 1, and then given angle theta, you can draw a point on that circle. This will be exactly e to the j theta. Simple examples for specific numbers: when theta equals to 0, e to j theta, it's e to the power of 0, naturally it's 1. E to the j pi, which is basically vector looking to the left, will be of course minus 1. E to the power of j pi over 2 will be looking to the up, which is 90 degrees, pi over 2 is 90 degrees. So it will be number j because it sits exactly on the imaginary axis. But you can find any other complex numbers on that circle for specific angles theta. Also you need to know that if you're adding to the power of exponent 2 pi k multiplied by j, this will give you always the same angle theta, which means e to the power of j theta plus 2 pi k j equals e to the power j theta, always, for any k which is 0 plus minus 1 plus minus 2 plus minus 3 and so on. Any whole number, any integer, for any integer k, this is true. Now we want to define absolute value. So absolute value of complex number a plus bj based on the Pythagoras theorem is just the radius r, and this is a squared plus b squared and square root of z. It's much simpler to do that, of course, for the representation in polar coordinates, because this is just r. How you get there? Let's say you have some complex number r multiplied by e to the power of j theta, and then you want absolute value of that. Since absolute value of multiplication is always multiplication of absolute values, this is absolute value of r multiplied by absolute value of exponent of j theta. Now, absolute value of r is clearly r, because r is positive always, or 0. And absolute value of e to the power of j theta is always 1. So if this is true, we get just r from all of that equation. Now, why is that true? Based on the Euler theorem, e to the j theta is basically cosine theta plus j sine theta. And absolute value of that rectangular representation of complex number, as we've seen before, is just square root of cosine square theta plus sine square theta. But this is trigonometric identity. We know that sine square plus cosine square equals to 1 always. So the square root of 1 is also 1. So that entire expression will be 1. So from geometric and from algebraic perspective, we can see that exponent of j theta with any theta will always have the radius 1. So the absolute value will be 1. Now, we want also to define conjugate. Conjugate is defined as a minus bj. Now, if you want to represent the same thing in polar representation, then it will be r to the exponent of minus j theta. Pay attention to the minus sign. This is conjugate to regular r multiplied by exponent of j theta, which means that in complex domain with rectangular coordinates, this vector will be just looking down from the vector which is looking up. So instead of going plus theta counterclockwise, you're going minus theta, which is clockwise, the same angle.